Back in 2017, something absolutely wild streaked through our solar system. For the first time ever, we spotted a visitor from another star. It was given the name Oumuamua, and honestly, it was a complete and total mystery. So today, we're going to play detective. We're going to follow the cosmic breadcrumbs this interstellar traveler left behind and see if we can solve the case. Where in the galaxy did it come from?
Really? This is the whole thing, right? The single biggest question. We had a messenger from a distant star show up on our doorstep for the first time in human history. The big mystery is, which star? That's the case we're about to crack open.
All right, so before we jump into the full-blown investigation, let's get properly introduced to our mystery guest. It all started on October 18, 2017. An observatory in Hawaii spots this tiny, faint speck of light, but it's moving in a way they've just never seen before. It became pretty clear pretty fast that this was no ordinary comet or asteroid. This was something else.
At first, you could imagine the scientists were just scratching their heads. Based on its path, they thought, okay, must be a comet. But when they looked closer, there was no tail, no fuzzy gas cloud. So a week later, they changed their minds. All right, it's an asteroid. But that didn't really fit either. This thing was so unique, they had to invent a whole new classification for it. I for Interstellar. And it got a name to match, Oumuamua, which is Hawaiian for a messenger from afar arriving first. How cool is that?
So how could they be so sure it wasn't from around here? Well, the proof is right here in the data. This is the orbital path they calculated. You can see how close it got to the sun, the angle it came in at, but one of these numbers is the absolute smoking gun. Can you see which one it is?
Yep, that's it, eccentricity. So think about it this way. Any object that's gravitationally stuck to our sun, a planet, an asteroid, whatever, its path is a closed loop, an ellipse, and its eccentricity is always a number less than 1. But Oumuamua's was almost 1.2, and that one little number changes everything. It means its path wasn't a loop at all. It was a hyperbola. It was never orbiting our sun. It was just passing through on a one-way ticket, confirming, without a doubt, that it came from somewhere very, very far away.
Okay, so it's official. We have an interstellar object. The real work, the real investigation can finally begin. And the crime scene? Basically, our entire stellar neighborhood. The challenge was just enormous. How in the world do you trace this tiny little rock's path backward in time through the mind-boggling vastness of the Milky Way? Well, here's how they did it. The scientists came up with this brilliant four-step process. First, they just collected all the data they could on nearby stars, where they are, how they're moving. Then, they built this complex computer model of our little corner of the galaxy, taking all its gravity into account. Now, step 3 is the magic part. They put Oumuamua in the model and essentially hit rewind, tracing its path backward for millions of years. And while the clock was spinning back, they watched for every single time its path crossed with another star.
And just take a second to let the scale of this sink in. They weren't just checking on a few dozen possible suspects. The team had to track the past movements of over 200,000 individual stars. Each one was a potential origin point for our visitor. This was a massive digital manhunt across space and time.
So the computers did their thing, they crunched all the numbers, and they came back with a long list of stars that had close encounters with Oumuamua's path. But just because their paths crossed doesn't automatically make one of them the parent star. The detectives had to start weeding out the false leads.
And some of these first encounters look pretty good on paper. Take HIP 3757. It passed within just 0.04 parsecs, which is cosmically speaking a stone's throw. But then, you look at that relative velocity, 185 kilometers per second. For Oumuamua to have been gently ejected from its home system, it would have had a very low speed compared to its parent star. Think of a boat just slowly drifting away from a dock. These high-speed passes, they're more like two speedboats blasting past each other in opposite directions. These were not the culprits.
And that right there became the golden rule, the single most important clue in the entire investigation. They weren't just looking for a close encounter. They were looking for a close, slow encounter, a moment where Oumuamua and the star were moving at almost the same speed, in the same direction. That's exactly what you'd expect if it had just been nudged out of that system.
So once they applied that low-velocity filter, everything changed. Suddenly, that massive field of over 200,000 stars of interest, it narrowed dramatically. All of a sudden, the list was down to just a handful of really promising candidates. This became the cosmic most wanted list. And here they are. Out of all those hundreds of thousands of stars, only a few had that magic combination. Just look at these relative velocities, all under 10 kilometers per second. Compared to those red herrings we saw before, this is a cosmic crawl. These are the stars we need to look at. So let's open up the case file on a couple of.
First up is the star GJ876. Now, this one looked really good. The relative velocity was super low, plus we actually know it has a planetary system with some really massive planets, which is exactly the kind of gravitational setup that could totally slingshot an object like Oumuamua out into deep space. But, the case isn't perfect. Even though the pass was slow, it still happened at a pretty large distance, and there's some tiny uncertainties in the data about the star's motion, which just makes the whole calculation a little bit fuzzy.
Then we've got this red dwarf star UCAC4 535-065571. It also has that nice low relative velocity going for it. The big problem here is the data quality. The scientists themselves said its motion is rather poorly known. Basically, to make this encounter work, they had to push the star's known speed and position right to the very edge of the margin of error. So, is it possible? Yeah, but it's far from a slam dunk.
And this is actually one of the plots from the research paper. It shows you what this cosmic backtracking actually looks like. You can see Oumuamua's past journey traced in that black line. The other colorful lines are the paths of our sun and a few of those suspect stars. The whole investigation is about finding the exact point where these lines got closest millions of years ago. So, after all of this amazing detective work, tracking 200,000 stars, running these incredibly complex models backward in time, sifting through all the evidence, what was the final verdict? Did they find their culprit?
Well, the researchers themselves put it pretty plainly in their conclusion. Even after finding some really tantalizing candidates, they just couldn't point to a single one and say, that's it, that's where it came from. The cosmic detective story, at least for now, remains an unsolved case.
And the reason it's still unsolved all comes down to precision. A tiny, tiny error in measuring a star's speed today blows up into a massive area of uncertainty when you try to project its path millions of years into the past. It's kind of like trying to pinpoint exactly where a car started a cross-country trip based on a 1-second blurry video of it flying by on the highway. But the good news is, the case isn't closed for good. Missions like the Gaia Space Observatory are creating this insane 3D map of our galaxy with precision we've never had before. That new data could be the key to finally cracking this thing wide open.
And that leaves us with one last really mind-bending thought. Oumuamua wasn't special because it was the only one. It was special because it was the first one we were actually able to see. It proved that these messengers from other star systems are really out there. So the real question isn't just where Oumuamua came from, but how many more are sailing through our solar system, right now, completely silent and unseen, each one carrying its own clues from a distant, unknown shore.